Hi guys, there's a few bits I want to point out today. So hopefully you've already done the large data set and tried to clean the data by removing any outliers. So the first thing I thought I'd do today is look at how you can mathematically calculate an outlier rather than just looking at it and saying, well, that looks too big or too small. There is a mathematical way. So what I've got here is a normal curve, and in the middle here, this is where your mean is. I've used x bar and also mu to indicate the mean. Now on a normal distribution, it's got very specific points here which lie within certain percentages of data. So this point here is mu plus sigma, and that point here is mu minus sigma. So if you took whatever your mean was and added on one standard deviation, you would get to this point here. If you took your mean and subtracted one standard deviation, you get to here. This point here is mu plus 2 standard deviations. This is mu minus 2 standard deviations. This is mu plus 3 standard deviations, and this is mu minus 3 standard deviations. Now we'll look more at this in the future when we actually look at the normal distribution. But a lot of data follows this kind of a curve. A lot of things that happen in nature. So for example, heights. So most people have a height which is around the mean plus or minus 1 standard deviation. These people over here will be like the giants, and these will be your dwarfs and your midgets. People's weight follows the normal distribution as well. People's IQ, loads of things follow that kind of distribution. Now, mathematically, 68% of the population would lie between the mean plus or minus 1 standard deviation. So that could be your people who are around the same height. Then between the mean plus or minus 2 standard deviations, you've actually got 95% of your data there. And the mean plus or minus 3 standard deviations, you've actually got 99.75% of your population there. So you can see anything that lies out here or here are very, very unusual values. Now, to work out an outlier mathematically, we normally use the mean plus or minus 2 standard deviations. So we're saying if a value lies in this region here or this region here, then it is classed as an outlier. So you take your mean, you take your standard deviation, times it by 2, add it onto the mean, take it away from the mean, and any values bigger than that or smaller than that, we say they're outliers because they only represent 5% of the population. Now to move on to something called linear coding. It's not as difficult as it seems, but sometimes we might deal with really large data. So linear coding tends to be when we've got really, really large numbers and we want to actually make them smaller. However, the numbers I'm working with today are particularly small anyway. But if you've got numbers in the hundreds, thousands, millions, and you want to work out the mean and standard deviation, you probably want to make them smaller. So that's when linear coding comes into it. But firstly, have a look at this data set. I've already worked out the mean for you, and I've worked out the standard deviation. Now if I subtract 2 from each of the elements, we've now got this data set. I've worked out the mean and I've worked out the standard deviation. Notice here that actually the standard deviation is the same, but the mean has also reduced by 2. So subtracting 2 from every value has caused the mean to go down by 2, which we'd expect, but the standard deviation, which is a measure of spread, has not changed. Okay, so have a think about that. Why would that not change? Well, if all of your values have reduced by 2, they're still the same distance away from the mean. So the standard deviation hasn't changed here. If we look at this data set again, same mean, same standard deviation, but this time we multiply it by 3, what you'll notice is the mean has times by 3, as we'd expect, but also the standard deviation has changed because we've now stretched the data, so it's more spread out. So, to summarise this up, if we've got the mean and our data is coded using a multiple and an addition, then if we've got a mean of x bar, the coded mean would be a times by your mean plus b. The mean is affected by multiplication, division, addition and subtraction. Your standard deviation, on the other hand, the coded standard deviation is only affected by multiplication and division. Okay? Right, let's have a go at an example. Okay, so we've got some data which is actually already being coded. So all of our x values have been multiplied by 1,000 and we've added 7 onto it, and then we've got our new data. So this here is my coded data. What I need to do, calculate the variance and standard deviation of x. Well, I'm actually not going to work out the variance. I'm going to work out the mean instead, because I want to show you how to do that. So we're going to the mean and standard deviation. So the first thing we need to do is work out the mean and standard deviation of our coded data. So our coded data y, to work out y bar, it's the sum of all of those values added together divided by how many there are. That's 110.4 over 60. I make that 1.84. Standard deviation for y, I'm going to use this formula because there's no other formula I can use here actually. If you try and use the other one, that requires you to take each value away from the mean. It's not going to happen. You haven't got that availability. I make that 2.96. So that's my coded data. Now I want the mean and the standard deviation of x. So the decoded data, if you like. Well, y bar is 1,000 lots of x bar plus 7. So if I want x bar, I just need to undo that. I need to take my y bar, take away my 7 and divide by 1,000, and that will give me x bar. My standard deviation, remember, it's not affected by addition or subtraction. So sigma y is 1,000 lots of my sigma x. So if I want standard deviation for x, I need to take my sigma y and divide it by 1,000. Okay? So the mean for the coded data is 1.84, so I would take away 7 and divide by 1,000. For my sigma x, I'd take my 2.96 and I'd divide it by, I can't quite fit this on. I'm just struggling here to fit this on. I'm going to move this further over, okay? So 2.96 divided by 1,000, okay? So I make that x bar comes out to be, it's something pretty small. I've got negative 0.00516 and I've got my sigma x to be 0.00296. So these are particularly small numbers, so you could probably see why we'd want to code that to make the numbers actually more manageable for us. Right, now have a look at your chapter checklist and try some of the questions from the linear coding exercise, which is on page 317. Best of luck.